Welcome! In this video, we'll be tackling problem number 7, reverse integer. This is a classic algorithmic challenge that tests your understanding of number manipulation and edge case handling. Let's dive in and explore the solution step by step. The problem asks us to reverse the digits of a signed 32-bit integer, which means the number can be either positive or negative. However, if reversing the number causes it to go outside the valid range of signed 32-bit integers, which is from -2 to the power of 31 to 2 to the power of 31, we need to return 0 instead of the reversed number. The input is a single signed 32-bit integer x, and the output is the reversed integer, provided it stays within the valid range. Let's look at an example. If the input is 123, reversing the digits gives us 321, which is a valid 32-bit signed integer, so we return 321 as the output. In the first example, reversing 123 simply rearranges the digits to form 321, which is within the valid range. So, the output is 321. Now, for the second example, the input is -123. Reversing the digits gives -321. Notice that the negative sign stays in its correct position, and since -321 is also within the signed 32-bit range, we return -321 as the result. Another interesting case is when the input is 120. Reversing the digits gives 021, but leading zeros are always omitted, so the output becomes 21 instead. Continuing with more examples, let's consider an input of 0. Since reversing 0 doesn't change anything, the output remains 0. Now, let's look at one more case where the input is a very large number, such as 15342364669. Reversing this number results in 9646324351, which exceeds the maximum value for a 32-bit signed integer. Since it overflows, the output must be 0. These examples highlight how we need to handle both valid and invalid cases while reversing the digits of the input. To summarize the constraints, the input x is always a signed 32-bit integer, meaning it falls within the range of -231 to 231. However, the reversed integer must also fit within this range. If it doesn't, we return 0 to indicate an overflow. Additionally, any leading zeros in the reversed integer are omitted. For instance, reversing 120 results in 21 because the leading zero is removed. Finally, we need to handle edge cases, such as detecting overflow when reversing very large integers like 15342364669 or -2147483648. Some other edge cases to consider include single-digit inputs like 0, 5, or -9. Since reversing these numbers doesn't change them, the output is the same as the input. Another important case is removing trailing zeros when reversing numbers like 120 or -450. For example, reversing -450 gives -54 because the trailing zero is dropped. Finally, if the input is 0, the output should always remain 0. These edge cases ensure that our solution handles all possible scenarios correctly. When solving the problem of reversing an integer, one of the first approaches we might consider is using string manipulation. The intuition here is straightforward. We can convert the integer into a string, reverse the string, and then convert it back into an integer. For negative numbers, we can handle the negative sign separately, excluding it from the reversal operation and then reattaching it afterward. The steps for this approach include converting the number into a string, reversing the string, converting it back to an integer, and finally checking if the reversed integer falls within the valid 32-bit signed integer range. If it doesn't, we return 0. While this approach is simple and easy to implement, it has some trade-offs. The time complexity is O(n), where n is the number of digits, because string reversal is a linear operation. However, the space complexity is also O(n), due to the storage requirements of the intermediate string. This makes it less efficient, especially for scenarios where numerical operations are preferred over string-based manipulations. Another, more efficient approach involves reversing the integer mathematically using modulo and division operations. The key idea here is to avoid converting the number into a string and instead extract and process each digit directly. To achieve this, we initialize a variable to store the reversed number. Then, we repeatedly extract the last digit of the number using modulo and append it to the reversed number by multiplying the current reversed number by 10 and adding the extracted digit. After processing the last digit, we update the original number by performing integer division by 10, discarding the process digit. One critical step in this process is to check for potential overflow before appending any digit. If adding the next digit would push the reversed number outside the 32-bit signed integer range, we return 0. This approach has a time complexity of O(n), as each digit is processed once, and a space complexity of O(1), because it doesn't require additional storage like strings. This makes it significantly more efficient than the string-based method. While there's also a recursive approach that performs digit reversal, it uses the same mathematical operations but adds recursive function call overhead. This increases memory usage, making it less efficient. The recursive approach, while elegant, comes with its own set of trade-offs. Specifically, the space complexity increases to O(n) due to the memory overhead from the call stack. This makes it less suitable for handling large inputs where memory efficiency is a priority. Now, shifting our focus to the chosen strategy, the mathematical reversal using modulo and division stands out as the optimal solution. This method directly operates on the number, avoiding string conversion and its associated inefficiencies. The process of reversing the digits is both time efficient and space efficient, as it works with the number directly and has a constant space complexity of O(1). A key observation here is that the reversal can be achieved by repeatedly extracting and appending digits using modulo and division. Importantly, overflow is managed dynamically by comparing the intermediate reversed number to a threshold derived from the 32-bit limit. This ensures that the solution handles edge cases like overflow and negative numbers seamlessly, without requiring additional complexity. While the mathematical approach is efficient, it does require careful implementation to handle edge cases, such as detecting overflow conditions and correctly processing negative numbers. These complexities are offset by the direct and computationally inexpensive operations it employs. By avoiding string manipulations and recursive overhead, this method achieves the best balance of efficiency and reliability. Ultimately, its combination of low time and space complexity makes it the ideal choice for solving the reverse integer problem, especially when working within the constraints of the 32-bit signed integer range. In this problem, we are tasked with reversing the digits of a given integer x, while ensuring that the reversed value stays within the bounds of a signed 32-bit integer. If it overflows, we simply return 0. To solve this, we can use a brute force approach that leverages string manipulation. First, we handle the input integer. If the value of x is 0, we directly return 0 because reversing it has no effect. For other values, we check if the number is negative and store its sign in a Boolean flag. This helps us process the number as a positive value by converting it to its absolute form. Then, we convert the absolute value of x into a string, as strings are easier to manipulate when reversing digits. Using Python slicing, we reverse the string representation of the number. For example, if x is 123, it becomes the string 123, and reversing it results in 321. If the input is negative, like -123, we ignore the negative sign during the reversal, so we still get 321 after reversing the digits. Once we have the reversed string, we convert it back into an integer. If the is_negative flag is set to true, we reapply the negative sign to the result. For instance, if the reverse string is 321 and the original number was negative, the result becomes -321. After obtaining the reversed integer, we need to ensure it falls within the valid 32-bit signed integer range, which is from -2(31) to 2 to the power of 31(1), or -2147483648 to 2147483647. If the reversed number exceeds this range in either direction, we return 0. Finally, if all these checks pass, we return the reversed integer as the result. This approach ensures correctness while handling edge cases and potential overflow scenarios. Now, let's discuss some key insights from this approach. First, why do we use string manipulation? Reversing digits is simplified by converting the number to a string, as string slicing in Python allows us to reverse it efficiently without additional loops or logic. Separating the sign handling from the reversal process makes the algorithm more straightforward and avoids unnecessary complications. Next, detecting overflow is a critical step. By directly comparing the reversed integer against the 32-bit integer boundaries, we ensure that no invalid results are returned. This safeguard is necessary for compliance with the problem constraints. We also account for important edge cases. For example, if x is 0, reversing it results in 0. Single-digit numbers like 5 or -5 remain unchanged after reversal. Numbers with trailing zeros, such as 120, lose those zeros after reversal, resulting in 21. Finally, for numbers like 15342364669, the reversal exceeds the 32-bit range, so we return 0 to indicate an overflow. To implement this solution, we rely on two main data structures. First, we use a string to hold the string representation of the number. Strings are ideal for slicing and reversing operations, which are central to our approach. Second, the final result is stored as an integer after converting the reversed string back. This ensures that the output matches the expected data type. Now, let's analyze the complexity of this algorithm. The time complexity is O(n), where n is the number of digits in the input integer x. This is because converting the number to a string, reversing the string, and converting it back to an integer all operate in linear time relative to the number of digits. The space complexity is also O(n), since the string representation of the number requires additional memory proportional to the number of digits. Overall, this is an efficient solution given the constraints of the problem. Let's go through an example to solidify our understanding. Consider the input x equals 123. First, we convert it to a string, resulting in 123. Then, we reverse the string, which gives 321. After that, we convert the reversed string back into an integer, resulting in 321. We check if this value is within the valid 32-bit range, which it is, so we return 321. Now, for a second example, let x equals -456. We treat the absolute value, so the string becomes 456. Reversing this string gives 654. Converting it back to an integer results in 654. Since the original number was negative, we apply the negative sign, making it -654. This value is within the valid range, so we return -654 as the result. Finally, let's analyze a more challenging case. Suppose the input is x equals 15342364669. After converting this to a string, we get 15342364669. Reversing the string results in 96463243551. When we convert this back to an integer, the value is 96463243551. However, this exceeds the upper limit of the 32-bit signed integer range, which is 2147483647. Therefore, rather than returning an invalid result, we return 0 to indicate an overflow condition. This example demonstrates the importance of the overflow check in ensuring the correctness of our solution for larger inputs. The solution starts by defining the 32-bit signed integer range, which is required to handle overflow conditions. The constants int_min and int_max represent the smallest and largest values within this range. This ensures that the reversed integer remains valid. Next, the code determines if the input number x is negative. This is done by checking if x is less than 0. If the number is negative, it sets a flag as _negative to true. This is important because the reversal process works with the absolute value of the number initially. The absolute value of x is then converted to a string, reversed using slicing, ::-1, and converted back to an integer. This effectively reverses the digits of the number. For example, if x is 123, the string conversion and reversal process would transform it into 321. If the input number was originally negative, as indicated by the is_negative flag, the reversed number is converted back to a negative by multiplying it by -1. This step restores the correct sign to the reversed integer. Finally, the code checks whether the result is within the valid 32-bit signed integer range. If the reversed number exceeds these bounds, the function returns 0. Otherwise, the reversed number is returned as the output. This implementation handles all edge cases, including input numbers with trailing zeros, e.g., 120, large numbers that may overflow when reversed, and negative values. It operates efficiently with a time complexity of O(n), where n is the number of digits in the input number, as the main operations involve string manipulation and basic arithmetic. Here, we begin the Java implementation of the reverse integer problem. First, we define the range of 32-bit signed integers, which is crucial because reversing an integer might result in a value outside this range. This is represented using constants int_min and int_max. Next, we initialize a variable named result to store the reversed integer, starting with 0. The while loop runs as long as the input x is not equal to 0. Inside the loop, we extract the last digit of x using the modulus operator, and then reduce x by dividing it by 10. Before appending this digit to result, we perform checks to ensure there's no overflow. Specifically, we compare result against int_max and int_min bounds to see if multiplying it by 10 and adding the current digit would exceed the allowed range. If an overflow is detected, we immediately return 0. Otherwise, we safely append the digit by multiplying result by 10 and adding the extracted digit. Finally, after the loop has processed all the digits of the input number, we simply return the result, which now contains the reversed integer. This concise implementation ensures that we handle both positive and negative numbers while preventing overflow, thanks to the checks we included during the process. The function is wrapped up in a public class named solution, making it ready for execution in the LeetCode environment or any other Java platform. To solve the reverse integer problem, we begin with the example where x equals 123. First, we define the boundaries for a 32-bit signed integer, which are -2 to the power of 31 or -214748364 as the minimum value, and 2 to the power of 31 1 or 214748364 as the maximum value. Since x is positive, we set the is_negative flag to false. Next, we calculate the absolute value of x, which is simply 123. By converting this number to a string, reversing the string to get 321, and then converting it back to an integer, we obtain the reversed number as 321. At this point, since the is_negative flag is false, we don't need to change the sign, so the reversed number remains 321. Finally, we check if the reversed number lies within the valid range for a 32-bit signed integer. Since 321 is well within this range, it is valid, and we can move forward. Here, the output for x equals 123 is simply 321, as determined in the previous steps. Now, let's consider another example where x equals -456. In this case, we again start with the 32-bit integer boundaries. int_min is -214748364 and int_max is 214748364. Since x is negative, we set the is_negative flag to true. Next, we take the absolute value of x, which is 456. We then convert this absolute value to a string, reverse the string to get 654, and convert it back to an integer. This gives a reversed number of 654. Since the is_negative flag is true, we restore the sign by negating the reversed number, resulting in -654. After reversing and restoring the sign for x equals -456, the next step is to ensure the result is within the valid 32-bit signed integer range. Since -654 falls within the range of -214748364 to 214748364, it is valid. Therefore, the output for this input is -654. Now, let's analyze an overflow case where x equals 153.423.6469. As always, we start by defining the 32-bit integer limits. Since x is positive, the is_negative flag is set to false. We calculate the absolute value of x, which is 153.423.6469. Converting this value to a string and reversing it gives 964.632.4351. Converting this reverse string back to an integer results in 964.632.4351. Now, with the reverse number for x equals 153.423.6469 being 964.632.4351, we check the sign. Since the input was positive, the is_negative flag is false, and the sign remains unchanged. The reversed number is still 964.632.4351. However, before returning this number, we perform an overflow check. Comparing 964,632,4351 to the 32-bit integer maximum of 214,748,3647, we find that it exceeds the allowed range. As specified in the problem, when the reversed number causes overflow, the function must return 0. Therefore, the output for this case is 0. In summary, the solution involves reversing the absolute value of the input, restoring the sign, and validating the result against the 32-bit integer range. If the result is out of bounds, we return 0. The algorithm operates with a time complexity of O(n), where n is the number of digits in X, and a space complexity of O(n), due to the string manipulation involved. To determine the time complexity of this solution, we can break it down into its individual operations. First, the absolute value computation, using abs, x, is a constant time operation, O(1), as it simply calculates the magnitude of the given integer. Next, converting this absolute value into a string using str, abs, x, takes O(d) the time, where d is the number of digits in the integer x, because each digit needs to be processed during the conversion. Then, reversing this string using slicing, ::(1), also requires O(d) time since it traverses all d characters in the string. After that, converting the reversed string back into an integer with int, again takes O(d) time, as every character in the string must be processed. Finally, the overflow check, which ensures the reversed number remains within the valid 32-bit signed integer range, is a simple comparison and takes constant time, O(1). Together, these steps form the basis for analyzing the overall time complexity of the solution. Adding up the individual time costs, we get O(1) for the absolute value computation, O(d) for string conversion, O(d) for string reversal, O(d) for integer conversion, and O(1) for the overflow check. This simplifies to O(d), where d is the number of digits in the input integer x. Since the number of digits d is proportional to log 10 x, derived from the relationship d equals floor, log 10 x, plus 1, we can express the overall time complexity as O log 10 x. Now, looking at the space complexity, the main contributor is the string representation of the number. When the integer is converted to a string and later reversed, it requires O(d) space, where d is the number of digits in the integer. In addition, intermediate variables such as is_negative, reversed_number, and constants like int_min and int_max each take up O(1) space, which does not scale with the input size. Importantly, the solution does not rely on any additional data structures that scale with the size of the input. This means the dominant space usage comes solely from the string representation of the number, which requires O(d) space. Since d is proportional to log 10 x, the overall space complexity is O log 10 x. To put this into perspective, let's compare this approach to more naive or brute force methods. A naive solution might involve repeatedly extracting digits from the number using arithmetic operations and appending them to construct the reversed number digit by digit. While this method would also have a time complexity of O(d), given that each digit is processed once, it could introduce additional computational overhead from repeated arithmetic and division operations. By contrast, the current approach is more efficient, as it takes advantage of Python's highly optimized string manipulation and integer conversion functions, making it both concise and easy to implement. Analyzing the best, average, and worst cases, the time complexity remains O log 10 x across all scenarios. This is because the solution always processes the entire input number, regardless of its specific value. Similarly, the space complexity is consistently O log 10 x, as it is dominated by the space required for the string representation, which scales with the number of digits in the input. To further solidify this, we can consider the mathematical foundation of the big O analysis. Let x represent the input integer, and let d be the number of digits in x. Since d is defined as floor, log 10 x, plus 1, any operation that involves processing the digits such as string conversion, reversal, or integer conversion is proportional to d. Consequently, the time complexity is O(d), which simplifies to O log 10 x, due to the logarithmic relationship between x and d. Similarly, the space complexity is also O(d), or equivalently O log 10 x, as it is determined by the string representation of the number. When working on the reverse integer problem, there are a few common mistakes to watch out for. One frequent issue is not properly handling negative numbers. For example, if you reverse minus 123 without accounting for the negative sign, you might end up with 321-, which is invalid. To fix this, you can separate the negative sign, reverse the digits, and then reattach the sign afterward. Another common pitfall is integer overflow. In languages like Java or C++, reversing a number could exceed the limits of a 32-bit signed integer, which ranges from -2 to the power of 31 to 2 to the power of 31. To avoid this, you should check if the result will exceed these bounds before appending each digit during reversal and return 0 for such cases. Additionally, using string conversion may seem simple, but it can introduce inefficiencies, especially for very large numbers. A better approach is to use mathematical operations like modulo and division for the reversal, which is faster. Finally, don't overlook leading zeros. For instance, reversing 100 might incorrectly yield 001, which is equivalent to 1 instead of the correct result of 100. Be sure your algorithm preserves significant digits even if there are leading zeros in the reversed number. It's also important to carefully handle edge cases. Examples include reversing 0, single-digit numbers, or the smallest possible integer, such as -2 to the power of 31. Failing to manage these can lead to runtime errors or incorrect results, so make sure to explicitly test and handle such scenarios during development. From an interview perspective, this problem is a great opportunity to showcase pattern recognition skills. Many reversal problems can be broken down into smaller, repeatable steps, such as extracting digits, reversing them, and reconstructing the number. Interviewers often prefer approaches that use modulo and integer division for reversal, as they demonstrate a solid grasp of mathematical operations and avoid the inefficiency of string manipulation. Discussing edge cases with your interviewer is also crucial. For example, bring up how you plan to handle negatives or overflow before diving into the code. This shows a thorough approach to problem analysis. Additionally, highlighting trade-offs between readability, like using string conversion, and efficiency, which mathematical reversal provides, can leave a positive impression. Finally, note that the time complexity for both brute force and modulo-based solutions is typically O(d), where d is the number of digits, since each digit is processed exactly once. This problem shares similarities with other challenges you might encounter. For example, palindrome number, which involves determining if an integer reads the same backward as forward, or +1, where you manipulate digits to increment an integer represented as an array. There's also multiply strings, which requires multiplying two large numbers represented as strings without directly converting them to integers. Exploring these related problems can deepen your understanding of digit manipulation techniques. As for alternative approaches, a brute force solution using strings involves converting the integer to a string, reversing it, and converting it back. While this is easy to implement, it's inefficient for larger numbers. A more optimal method is mathematical reversal, which uses modulo and division to iteratively extract digits and build the reversed number without any string conversions. This approach is fast and avoids unnecessary overhead. Another option is recursive reversal, where you process one digit at a time through recursion. While this can be elegant, it's less practical for very large numbers due to the risk of stack overflow. In terms of trade-offs, string-based methods prioritize simplicity and clarity but sacrifice performance. Mathematical approaches offer better efficiency but require careful handling of edge cases, such as overflow. Recursive solutions, while clean conceptually, are generally constrained by stack size and are less suitable for large inputs. Great job! To recap, we solved the reverse integer problem, covering edge cases and leveraging string manipulation for simplicity. Remember the importance of handling exceptions like overflow and negative numbers. Thanks for joining, like, subscribe, and stay tuned for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!